Here's video 2 from class 21. We were talking about using the Gibbs equations, and then we were talking about the entropy change of a solid or a liquid. This is the entropy change of a solid or liquid example 6.3. 1 kilogram of liquid water is heated from 20 degrees Celsius to 90 degrees Celsius. We want to calculate the entropy change, assuming constant specific heat, and then compare this to the result that we would find from the steam tables. Now, they don't say what the pressure is, but they do say it's liquid water. So we're basically going to have to stick with an assumption that it's going to be the S. See, I just lost it right here. Oh, okay, I see it. I was going down there. We're going to take the SF at those two different temperatures. First, let's see. They told us the first thing was to take a constant specific heat. So let's go to the table A4, and this is for water, and we have the specific heat. Now they're saying CP here, but we're going to call that thing the same thing as CV. All right, they're not going to be different from each other. So here we got water is 4.18. That's just this, the specific heat of water. And so let's go to here. Whoops. Yeah, that was from the last class, but we will. I don't know if we will use that or not. Let's see if we can. All right, so we looked up and found that C, I'll just call it C, is 4.18 kilojoules per kilogram degree Kelvin. And the equation that we're going to use, we just saw that a second ago, that was just right down there. We're going to say, here's the change in specific heat. So there you go. We're going to say that the change S is going to be CV ln T2 over T1. And so if we plug all those things in there, remember that these need to be, in order to do these kinds of relationships right here, we need to have, we're in Kelvin, so everything has to be absolute. So delta S is going to be 4.18, which is in the units we want, kilojoules per degree, kilogram degree Kelvin. That's the units we want for here. But we need to be able to get these ratios correct. We need to take our 90 plus 273 divided by 20 plus 273. And if we plug all those numbers in, 0.8955 kilojoules per kilogram degree Kelvin. Recall, though, that every time we do this, we're using one of these constants, it's an approximation. It might be a pretty good approximation. We might even found it's really, really darn close. But to be understand that that's always the approximation. But if you look something up in a table and you're actually able to find it, you could be pretty certain those are the values. If you have to interpolate, that's going to be a little bit of an approximation because you're taking something that isn't necessarily linear and you're taking a linear between 2 points. So there's some approximation built in there. So let's take a look at table B.1.1 and at the two temperatures, right? So we'll go at T equals 20 degrees, and we'll find the fluid specific, entropy. And then we'll also find it at, so this is 1 and this is 2, at 90 degrees Celsius, we will find the SF for each of these. So let's see, I'll go to this, and they should be on this next page right here, right? Where we have entropy, and here's our 20 degrees. So let's see if I did this one right. I'll just highlight it, and then a little bit upwards right there, and it should be this one. Let me just take a look at my notes and see, did I get them right? I sure did. Okay, so we have 0.2966 and 1.1924. I find that I think there's in some books they have a different reference for their entropy, so be on the lookout for not being the same from one book to another. But I'm not sure that's true of the steam tables. I know those are for refrigerant, but these two, we just looked these up. for fluids. So we might be on the lookout for other instances. So we see that we have the change, which is going to be S2 minus S1. And so 1.1924 minus 0.2966. And what we end up with is 0.8958 kilojoules per kilogram degree Kelvin. And we were pretty darn close, right? We're just like 3/10,000ths off, I guess. I found that we were less than, we're like 0.036% difference. That's a small amount of difference. So, okay. Let's see. I guess we'll do the next. I'll do the next section, and then we'll do some examples. Right. So this was just for a departure from what we from video 1, what we had covered, and we just wanted to do an example that corresponded with section 6.5. Now we're going to do stuff that we're going to go deeper dive into section 6.4. So stay tuned.